All right. Hello, everyone, and welcome back to our weekly Physics 8A live stream. Midterm season is upon us, so things are getting pretty busy. But this week we need to keep moving and talk about fluids. So we're going to be starting this new chapter and, in a sense, almost an entirely new part of 8A. All the stuff that came before this was mechanics, by which I mean Newtonian mechanics, and it kind of all fit together. And we learned about two types of motion, linear motion and rotational motion. And we have all the kinematic equations and work and energy and all the stuff. And it kind of is one big consistent whole. And there's other things we need to learn about in Physics 8A that are not necessarily mechanics, although they tend to fall under the umbrella of mechanics. So yes, fluids is really fluid mechanics, and oscillations and mechanical waves are part of mechanics, because they're closer to that than to anything else. Thermo is a different story. Thermo we can kind of set as a category of its own. But what I'm getting at here is that starting today with fluids, we're going to be dealing with chapters that are very much self-contained, that don't kind of blend all together like the previous chapters did, which can be good or bad. It depends on how you look at it, but I think it's more of an upside than a downside, in the sense that things become a bit more like a checklist at this point, a little bit more plug and chug in some ways, certainly thermo for sure, fluids to a degree. And you can, if you get really good at fluids, then, well, you go do oscillations and it's something completely different. So maybe that's a bummer that you don't get to kind of leverage you being good at fluids to help you with oscillations. But on the other bright side is that, just these chapters that you have to get good at, and they are what they are, and there's only so many things we can ask you in each chapter. So it's a little easier, I think, in that sense. And particularly waves are conceptually difficult, but practically very simple, and thermo's great. Thermo is extremely straightforward. So, and fluids aren't bad at all. Fluids it's a very short chapter. You could argue that it shouldn't even be there. It's a little weird. But they behave so differently from all the mechanics that we just learned about that they're here to kind of tell us that, well, okay, careful, not everything behaves like a rotating pulley or a block on an incline, and fluids are very different in that sense. So we're going to go over fluids. We're going to do a quick recap. There's basically 4 formulas that we need to know with a few other definitions, and so it's pretty quick. And we'll do a couple of very classic problems to illustrate how you might apply this knowledge to fluids problems. But fluids it's one of those chapters where it doesn't take a lot of time to get really good at it, because it's just so limited that there's not that many questions that we can ask you. So with that said, let's just dive into a quick recap about fluids at rest first, and then we'll do fluids that are flowing. Important to separate the two because they don't behave the same way. And for those of you who are joining us for the first time, welcome. And we do this live stream once a week to go over the topics of the week. And that's the important topics that you need to know about, and a few classic problems that that are worth having seen to kind of reinforce the concepts and to learn how you think through problems. That's kind of the goal here, is to be a stepping stone to harder problems once you kind of see how to set up problems and do maybe the more classic, not necessarily straightforward, but certainly more classic and more manageable ones. So, and all of this is on the website. So if you go to slackademia.com to the study guides, you can enroll in this class for free. Has everything plus the homework solution, so feel free to check it out. Okay, so fluids, basically the organization of the chapter is that there's fluids at rest and fluids that are flowing. And so let's just do a quick recap, and we will start with, in fact, even before we start with fluids at rest, let's start with a couple definitions. There are 2 new quantities that need to be introduced to deal with fluids, because the problem of a fluid is that, when I have a block on an incline, I can say the block has a mass of 2 kilograms. Like, okay, that's the block, and it's 2 kilograms. Fluids are tricky because the mass that I have is, well, depends on how much fluid I have. Do I have a bucket of it? Do I have a tank of it? How much fluid do I have? So it's not a very useful quantity to talk about mass. We prefer to talk about mass per volume, which is mass density. So mass density is rho. And that's going to be the mass of fluid divided by the volume that it occupies. So this is kilogram per cubic meter, are the units. And there's a couple of mass densities that you should know. Certainly the mass density of water you should know. So rho water, now water meaning liquid water, is 1,000 kilograms per cubic meter. That's the reference. Okay, we chose water as a reference. And then rho air is it's approximately 1.2 kilogram per cubic meter, although the truth is it depends on temperature quite a bit. So, but call it 1.2, like order of magnitude in your head, it's 1,000 times smaller than rho water, right? So it's much less dense than water. And I say that in preparation for the first problem that we'll do, because it's something that we need to acknowledge and we need to understand what the consequence of that is, particularly when it comes to the buoyant force. So we'll talk about that later, but those are two values. I mean, 1,000 kilograms per cubic meter, nobody has to give you that. Let's assume that you know that. And then rho air, you would be given if needed, but you should know it's about 1,000 times less. Okay. And so the other the other quantity, I should say, that we need to define, other than mass density, is pressure. So the thing about, again, a block, as we've treated blocks as point masses. That's what we said all along. We don't care about the shape, we just treat it like a point. And so all the forces applied to the block are applied to that point, which is fine. Like, that works really well. Well, again, when it comes to a fluid, it's how much fluid do I have, right? And I don't have a point of fluid, right? I have a certain amount, a certain volume, and unless I have only one particle of fluid, which would be my only point, you kind of argue that that's not really fluid. Like, you need more than that to say that, you can't put one particle of water in a glass and say you have a glass of water. That's nonsense. So you have a certain amount, a certain volume of fluid that you need to deal with, and the forces are going to be exerted not on a point, but rather on a surface. And a force exerted over a surface is a pressure. So capital P is pressure. That's force divided by area. In terms of unit, it's newtons per meter squared, which is the same as Pascal. And so Pascal is the proper unit of pressure, and it is a force over an area, right? And I try to make sure that my capital P is discernible from rho, because they don't represent the same thing, but they often happen to be in the same equation. So you got to be careful about that. Now, in terms of known pressures, you should probably know the atmospheric pressure. So, I mean, if you want the exact value, that one would be given. It's 1.01325 times 10 to the 5 Pascal. Nobody expects you to remember that, but you are expected to know that it's pretty much 10 to the 5 Pascal for all practical purposes. Okay? So those are the two new quantities that we need to introduce in order to properly describe fluids. In terms of mass, we have rho, it's mass per volume, and in terms of force, we actually have force over area, which is pressure. All right. So from there, let's first start with fluids at rest. Okay, now there's two equations for fluids at rest. And again, we're not trying to rederive everything and talk through everything in detail like in lecture. We're just trying to point out the formulas that you absolutely need to know to be able to do problems. Okay, so a fluid at rest, let's take, a lake or a swimming pool or a body of water, although it doesn't have to be water, but most of the time it is because it's just very relatable to use water in problems. And so we have some swimming pool or some lake, and let's say that it's at rest, right? So there's nothing crazy going on, like there's no waves or anything wild going on. And we have a point here, B, where we want to know the pressure. This has rho water or rho fluid, whatever, the mass density. And point B is a certain depth below the surface, call it H. And now typically we relate it to point A at the surface. Now it doesn't have to be the case. I could relate point A here to point B here if I wanted to, right? But typically we relate it to the pressure at the surface because we actually know what the pressure at the surface is. Certainly if it's a swimming pool or a lake, then the pressure at the surface is the atmospheric pressure, right? That's just PATM, whatever that is. Now, if this is a rice cooker that's, closed up and sealed tight, then okay, it's probably not PATM, it's pressure of the cooker, whatever it is. But okay, at the surface of the water here, the pressure is the surrounding pressure. And if it's a lake or a swimming pool, the surrounding pressure is the atmospheric pressure. And so pressure increases with depth. I think hopefully everybody agrees with that. If anything from experience, the deeper you go in the swimming pool, the more you feel the pressure acting on you. And pressure increases with depth proportionally to H. And so the pressure at point B is going to be the pressure at point A plus rho water gravity times H, which is, in this particular case, going to be PATM plus rho water GH. Right? But the formula that I'll box is just the formula with PA, because again, it doesn't have to be the case that PA is PATM. It is here, but doesn't have to be the case. Okay, so what's interesting is that it only depends on the depth. It does not depend on the shape of, let's say, the container, right? If you had a vase like this, right, with point A and point B like this, or one like this with point A here and point B here, the pressure at point B in both cases, if you fill this with the same amount of water in terms of height, right, so you level out the heights, same pressure at point B. The point B does not care about the shape of the container, right? So it is only depth that matters. Okay, so pressure increases with depth, and PB is PA plus rho water GH, or rho of whatever fluid. If this is something else, you plug in the right mass density. There we go. That's the word I was looking for. So there's really no name for this equation. Like, it doesn't have someone's name. I call it the hydrostatic pressure equation. So if you hear me say that, this is what I'm referring to. But I mean, it doesn't have an official name. Whereas we're going to talk about the buoyant force in a second, and that has a specific name, which is the buoyant force, of course. But this just tells you that pressure increases with depth. Okay. So now, let's say we had a swimming pool there for a minute above in our example. Now you take a basketball or a volleyball or something that you know will float if you throw it into the swimming pool. And, well, you throw it into the swimming pool. Okay? And it'll float, something like this. Okay, now the reason that it floats is directly related to the fact that pressure increases with depth. Okay? Now pressure can only push, right? So what's happening is that the fluid particles here are going to be pushing on this basketball that you just threw into the water, right? But the way that they push, if we zoom in real quick, they're going to push perpendicularly to the surface. But I'm making my arrows bigger and bigger because the deeper I go, the greater the pressure. Right now, this might not be a very big distance, right? It's a few inches perhaps, but okay. Point is, the deeper we go, the greater the pressure. And so we end up with something like this, where if you add them all together, the net effect is to exert a force that is upward, called the buoyant force. And it's really the water saying, like, you know, get out of there. Like, we were fine without you in here, basketball. We would like to return to where we were, but you're in the way. We're pushing on you. And, you know, depending on how heavy or lightweight you are, us pushing on you with a certain amount of pressure, therefore a certain amount of force, is going to force you to try to, you know, leave and float to at some point, right? So you get what's called the buoyant force because the pressure increases with depth, and it's going to basically push the ball upward. Now the buoyant force is given by FB. Now FB is rho fluid, G times the displaced volume. Now, I don't like the displaced volume. I've always found that that term made no sense. It's the historic term. What it means is the volume of water that was displaced by the basketball. In other words, there used to be water there. Now there's basketball occupying that volume where there used to be water. It displaced water out of that area, out of that volume, and so your V displaced is basically, it's the submerged volume. And so since that makes a ton of more sense, at least to me, I tend to call it the submerged volume. Okay, so whatever volume is submerged in the fluid, in this case, this volume right here. Okay, but it's the same thing as the displaced volume. Okay, now in this particular case, the fluid is water, so it's going to be rho water G V submerged, right? But here I'll box the more generic equation where we have rho fluid instead. Well, the point is, it's a function of the mass density of the fluid in which you put the object and also how much volume is within the fluid, underwater if it's water. Okay. Now it turns out that this volume here, the submerged volume, can increase, right? If somehow you manage to pull the entire basketball underwater, now we go from V submerged being a little less than half of the volume of the basketball to being the entire basketball. So it means that there's such a thing as a max buoyant force, right? Now I'll put it down here. This is just worth noting. The max buoyant force is going to be rho fluid times G, and the biggest V submerged can be is, well, the volume of the entire object. So that is the max buoyant force. And that is what you get once your entire object is submerged. Now it is what it is. If it's not enough to make you float or rise back up to the surface, then you're going to sink. For instance, a brick, even if you submerge it entirely and you get the max buoyant force, well, its weight is still going to be greater than the max buoyant force, so the brick is going to sink to the bottom of the ocean floor, right? But if you did this with the basketball and you had the max buoyant force acting on the basketball when it's entirely submerged, well, if you let it go, the basketball is going to rise to the surface. It didn't need the entire FB max force to float. In fact, it only needed this much to float. So it's going to rise back up until V submerged is this, and then it's going to float at the surface. All right, so that's the buoyant force. So it's a new force, and it comes from the pressure forces acting on the basketball. And as complicated as it seems like it might be to evaluate pressure forces, it turns out that if you do the math, you end up with a formula that's extremely simple and really nice. It's very straightforward to compute the buoyant force, right? Okay, so those are my two equations for a fluid at rest. So if the fluid is at rest, likely that you're dealing with one of these two or both. Not all fluids are at rest, so let's look at fluids in motion or fluids that are flowing. And we also have two equations in this case. Okay, so the first one is going to be what's called the continuity equation. All right, so I'm going to make a copy of that. And let's say we have a hose, maybe like a fire hose or something like that, and it gets narrower, right? So it's quite large here. It has a big cross-sectional area, but then the cross-sectional area gets smaller. So this is going to be A1, and this is going to be A2. And we have water flowing through this thing. Okay. Now it turns out that we say that water is an incompressible fluid. So if you apply some pressure to it, it doesn't change the volume. The volume is the volume. And because of that, the volume is conserved. So the volume coming in from the left is going to have to exit on the right. It has nowhere else to go. But because A2 is smaller, it actually has to exit faster. Now, if you've ever pinched a garden hose, you know exactly what I mean, right? It speeds up the water as it comes out. Okay, so if this is V1, then here I have V2. Now, the continuity equation tells me that A1V1 is equal to A2V2. Okay, so yes, if A2 goes down, V2 goes up. Simple as that. The entire volume coming in here every second has to exit every second on the right. The water has nowhere else to go. Okay, so that's the continuity equation. Pretty straightforward. Really not much to it, and it's an interesting thing to note because it goes back to what I was saying earlier. We have this chapter here because fluids just don't behave like other things, right? If this were a highway and you went from 4 lanes to 2 lanes, you would immediately get a traffic jam. Cars would slow down, right? Well, when it's a fluid, it's the other way around. I mean, there's less room for the fluid to flow, so it flows faster out through the cross-sectional area A2. So obviously fluids are different from cars, I get that. But the point is, this is part of the reasons why we have to study fluids, because if you didn't know that, you might not predict that behavior. So it's something that's worth noting. Now, while we're talking about continuity, I'm going to add another definition here. It's going to be called the volume flow rate. Now, the volume flow rate, typically denoted by Q sub V, is A times V, and that's in meters cubed per second. So it's how much water enters or exits every second. And in fact, if you look at it, the continuity equation just tells me conservation of flow rate. This is water coming in volume every second. This is volume of water leaving every second. Okay, I say that because a lot of times we just don't mention volume flow rate. It kind of gets brushed under the rug, and then invariably there's always a problem in fluids where it ends up showing up. And if you don't know what it is, then it's a bit of a bummer. Like, it's not complicated, it's just A times V. Turns out you kind of already know what it is, but until we point out the connection, it's not necessarily obvious. Okay, so volume flow rate is just how many cubic meters flow in or out every second. Okay. And so then the second equation to describe fluids in motion is going to be Bernoulli's equation. Okay, so let's imagine I have a pipe does something like this. It's larger at the base and it gets narrower up here. Then BA2, BA1, and I have water coming in like this and then exiting here. That's V2. Okay, so this is full of water. Okay. Now there's also going to be a change in height, right? The change in height is going to be H maybe. So maybe we call this H. Now typically we go from the center of the flow to the center of the flow, right? And so that's going to be an increase in height H. And Bernoulli's equation is effectively conservation of energy, but per volume. So it's energy per volume that is being conserved. And by the way, we know V2, just move this over real quick, V2 should be bigger than V1, yes? Because A2 is smaller than A1. Okay, so even though the fluid went up, now it leaves faster than it came in. Okay, interesting. And so Bernoulli's equation is P1, the pressure at point 1, plus 1/2 rho V1 squared. That looks exactly like kinetic energy. It's kinetic energy per volume. It's called kinetic pressure. Plus rho G, well, I'll call it H1. Right. And then P2 plus 1/2 rho V2 squared plus rho G H2. So it looks like 1/2 mv squared plus mgh, right? The only thing that's new here is pressure. That is because fluids flow from high pressure to low pressure. Right? They get pushed by pressure toward low pressure. Okay, so there is no such thing as a suction force, right? If you turn on your vacuum, is that actually sucking in the dirt from the ground? It is that the pressure inside is lower, so the atmospheric pressure pushes the dirt in and up the tube of the vacuum cleaner, right? But there is no such thing as a suction force. It does not exist, right? It is a difference in pressure. Pressure inside the vacuum is less than the pressure outside. Okay, now real quick, here we know that V2 is greater than V1. We also know that H2 is greater than H1, right? So if I write P1 plus 1/2 rho V1 squared plus rho G H1 is P2 plus 1/2 rho V2 squared plus rho G H2. This term is bigger than this one. This term is bigger than this one, right? That means that P2 has to be less than P1. Okay, so this is bigger than rho GH1. This is bigger than 1/2 rho V1 squared. And so the conclusion is that P2 has to be less than P1. Okay, so that's something to keep in mind. Pressure drops when velocity increases. That's what Bernoulli's equation tells us. Pressure drops when height increases too. Okay, so something to keep in mind. All right, so that's Bernoulli's equation, along with continuity equation, tells me all the equations that I need to describe fluids in motion. Is there more to fluids than this? Of course there is. You could spend 2 semesters studying fluids, and it's going to take you places you probably don't want to go. Ask me how I know. But the point is, this is all we study. Right? Again, it's a very short chapter. It's there to acknowledge the fact that fluids behave differently than blocks on inclines or rotating pulleys. And okay, we have to learn about them to an extent. I mean, they're quite important, and they are their own thing. Right, so you should at least know how ideal fluids behave. All right, so with that said, let's do 2 problems that are, I mean, they're so classic it's not even funny. They're foundational each in their own category. We'll start with fluids at rest, and then we will look at fluids that are flowing. In both cases, these are very, very classic problems that tend to be a foundation for other problems that build off of these or are variations of these. Okay, so they're very important problems, and we should spend the time needed to explain them completely. Okay, so we have an iceberg which has a mass density of 900 kilograms per cubic meters because it's made of ice, and a total volume of 2,000 cubic meters, okay. And it's floating somewhere cold, okay, and it has a certain volume that is submerged, and it's literally called V-submerged, which is convenient. And we want to, given a mass density of water and of air, and we'll see why air matters, well, actually, why it doesn't matter is what I should say. But we want to prove that 90% of the iceberg's total volume is underwater, which is something you hear all the time. It's about right, but let's prove it, okay? With our simple knowledge of fluids and our simple models, let's get to that 90% mark. Okay, so let's think about this. The iceberg is floating, okay, and we're assuming it doesn't bob up and down or anything weird. It's just there, it's floating. It's massive enough that it just stays in place. So it's in equilibrium, is what it means. In other words, the vertical forces cancel out. F net y is 0. Well, a good question is, what is F net y? What is it made up of? Okay, well, I mean, there's got to be the weight of this thing, right? There's got to be mass of ice times g, and I'll come back to that in a second. But if I were to draw a weight force, I would draw it like this, and I would call it m ice times g. All right. Now there's got to be an upward force, otherwise this thing sinks to the bottom of the ocean. And of course, we just learned about the buoyant force. So we're like, well, there's got to be a buoyant force because there's a certain amount of this iceberg that is submerged underwater, right? So here we can say that there's got to be a buoyant force going to point up, right? Buoyant forces always point in the direction of low pressure, right? So pressure is higher here than here, so the buoyant force points straight up. The buoyant force FB, by definition, is rho of water, G, times the displaced volume or the submerged volume. Okay, well, I'm told that the submerged volume is called V submerged, conveniently. So that's it. That's my buoyant force due to water, or from the water. Okay. Now we said buoyant force arises when you place an object in a fluid and it displaces some of that fluid, and that fluid therefore tries to push on the object to get it out of there and creates a buoyant force. Well, the fact that there would be a buoyant force due to water, we're like, no, yeah, I mean, that makes sense. But one could argue that there's also a buoyant force due to air, because part of this iceberg is submerged in air, right? It occupies a certain volume in the air. So that is true. There is, in fact, a buoyant force due to air, which, now careful, it also points up. Now this confuses everyone, even though the air, like, but it pushes down. Like, what are you talking about? It's like, no, I get it, but it pushes on down on the water too, and that ends up affecting the pressure. At the end of the day, the easiest thing to remember to not get completely confused is that buoyant forces point toward low pressure. And low pressure is up, including in air. That's true, right? You know, as you rise, pressure drops. So the buoyant force from air, FB air, is going to point upward. Now, what is that equal to? Well, with the same logic, it ought to be rho of air times G times, now the amount, the volume that's in air is the total amount of volume, V total, minus V submerged, actually. That's the difference between the two. That's going to be this volume here. Okay. Now, there absolutely is a buoyant force due to air. The thing is, it's absolutely useless, right? It's useless because the mass density of air is pretty much 1,000 times smaller than the mass density of water. Okay. Not only that, but if this is really 90% of the total volume, this is 10%. So now 10% is 0.1 times rho air, which is 1,000 times smaller. We're getting a buoyant force from air that is 10,000 times smaller than the buoyant force due to water, and which makes it completely negligible, right? In other words, put simply, the iceberg floats because of the buoyant force due to water, not because of the buoyant force due to air. Okay. And so this is a very important thing to acknowledge, which is that because rho air is so small in front of rho water, we neglect the buoyant force due to air in front of the buoyant force due to water. Okay, now, so that's important, first of all, meaning that if you look at solutions to these types of problems, you will very likely never see the buoyant force due to air. We're like, yeah, I know it's there, but I don't care. It doesn't make a difference. It's 10,000 times smaller, or at least 1,000 times smaller, like rounding error. I don't care. So that's why we usually don't draw it. So that, first of all, is important. Second of all, I did not say that we neglect the buoyant force due to air, period. I said we neglect the buoyant force due to air in front of another buoyant force that is 1,000 to 10,000 times greater. Okay, so you don't just get to neglect stuff in physics, you get to neglect something in front of something else. Okay, your savings can be neglected in front of Bill Gates' savings. You don't make a difference, I'm sorry. And if you do, call me. But you probably don't make a difference. So the point is, but we're not saying that your savings are irrelevant, because like, fuck that, they're relevant to you. So we're just saying in comparison, though, there's no comparison, right? Like Bill Gates' fortune compared to your savings, it dwarfs it completely. It's not going to change his life to get your savings. Okay, so you get to neglect something in front of something else. You don't just get to say we neglect your savings. They don't exist. Or you get to neglect FB air. It doesn't exist. Okay, so and I say that for a very simple reason, is that there are problems in physics where it turns out the buoyant force due to air is everything. For instance, how do you think a hot air balloon floats? Well, it's because of the buoyant force due to air. By the way, that's the only buoyant force that you have in that problem, right? So if I only have the buoyant force due to air, I don't get to neglect it. There's nothing in front of which to neglect it. If I neglect it, the hot air balloon falls. And there are no hot air balloons in the world. They don't take off. Okay? So I know I'm beating a dead horse probably, and I'm almost going down a rabbit hole, but it's really important. Like you get to neglect something in front of something else. Okay? But you can't just neglect something, period. So the buoyant force due to air, in certain cases, is extremely important. It is the only reason why something might happen. However, if we're talking about an iceberg floating in the water, or we're talking about a boat floating in the water, or a basketball, whatever it is that's floating at a surface of the water, the buoyant force due to air can be safely neglected because the buoyant force due to water will always be so much bigger. Okay? So, I'm going to write F net y equals 0 because this thing is in equilibrium, and I'm going to neglect the buoyant force due to air in front of the buoyant force from the water. So F net y is going to be 0. That's going to be FB minus M ice G is equal to 0. Okay. I would be done, except I don't know the mass of ice, which is very typical in fluids problems to not give you mass. Instead, we prefer to give you volumes and rho, like the mass density. Okay, well, I know rho of ice, right, which is mass per volume. So
how do I get mass from mass density? Well, I take mass density, rho of ice, and I multiply by the volume. By the way, the volume of ice, which is the total volume of the iceberg, right?
So mass of ice is rho ice v total.
Okay, so then I get a buoyant force that is rho water g v submerged is equal to rho ice v total times g. G goes away, and I find that v submerged over v total is equal to rho ice over rho water. That's 900 over 1,000, which is 0.9. In other words, V submerged is 0.9 times V total, which is 90% of V total, just to be clear.
Okay. So, yes, it's a very simple derivation, but there was quite a few things we needed to talk about before we got there. Right? In particular, the fact that the buoyant force due to air can be safely neglected. Okay. Okay, so that's a classic. It's a good thing to keep in mind when dealing with buoyant forces. And if you have the buoyant force due to air, you can probably neglect it in front of the buoyant force due to water for an object that's floating in water. Okay. Now, let's move on to fluids that are flowing. This problem is everywhere in one form or the other. It's even in the lab, and it's such a classic problem that we have to do it. We have to understand how to approach it, and then from there you can always add on to it. Right? So there's a lot of different ways that you could add on to this problem, but you could put a hose that connects here and drains somewhere lower. Maybe the hose gets narrower and narrower, or you could put a longer pipe here with a standpipe with a certain amount of water in there to read pressure, so on and so forth. There's a whole bunch of ways that you can tweak this problem, but the baseline is the same. And so we have a large tank. It's open to the atmosphere, and it stores a certain amount of water. We know the radius r and the height h. And we are told that the tank has a little spigot at the bottom for draining purposes. Maybe you want to empty the tank and clean it now and then. And the spigot is open, allowing the water to flow out. And we're told basically that the spigot has a radius little r that is very, very, very small in front of big R. Right? Now this is very common. You typically have an opening that is going to have an area that's very small compared to the other area involved. Now we need to talk about what those areas are and how we figure out what that means, but let's first start by drawing out what happens in a scenario like this. Okay, so if you open the spigot, water will flow out, okay. And eventually a fluid particle here at point, call it 1, is going to follow a path maybe like this. Something like that. And it's going to flow out. It's going to flow out with a speed v2. This is going to be 0.2. Now you might say, well, how do you know the shape? I don't really know the shape. The exact shape of this dotted line doesn't actually matter. What matters is that the dotted line connects point 1 to point 2. Because just like conservation of energy, you apply it between the beginning and the end, or what you call initial and what you call final. Right? You don't actually care what happens in between. You just evaluate energy at the beginning, evaluate energy at the end, and you set them equal to each other. Right? And that's what I'm going to do with Bernoulli. So I don't really care what this dotted line looks like. I just care that it connects the free surface here open to the atmosphere to the spigot, and the water flowing out of it. Okay, now if this is what I'm choosing for points 1 and 2,
then, okay, the area here, A1, is pi r squared, okay? And here the area A2 is pi little r squared, okay? And by the way, if I have little r is very small in front of big R, that means that little r over big R is going to be very small in front of 1.
It's going to be a very small fraction. Okay. And well, I drew V1,
okay, but the truth is this water level is going to drop, yeah, and so
V1 is going to look like this. So this is V2 as I exit. This is V1, which is basically the speed at which the water level drops. Okay. What is the volume flow rate of the water exiting the tank? Okay, good question. I mean, I kind of know the answer, right? Like QV is AV, so it's going to be A2V2. Right? I know A2, so okay. I don't know V2, so I'm going to have to find V2. Okay, but okay, like that's where I want to go with this. I want to find V2, multiply by A2 to get the volume flow rate. Okay. So let's put this up here. We have a fluid that is flowing, and so we only have so many options. We have the continuity equation, and we have Bernoulli's equation. Usually, if you write both, you end up solving, because that's all you have, right? So you write all the equations that you can, and then you should have enough equations to solve. Now, there's a specific way in which we're going to solve this thing that has to do with the fact that A1 is much bigger than A2. Okay, so here, just to be clear, y2, we're going to make that 0. And y1, we're going to make that h, just so that we can have everything in front of us that we need to write continuity and Bernoulli's equation. Okay, so the continuity equation is going to tell me that A1V1 is A2V2. Okay, so V2 is going to be A2, no, A1, duh, obviously, over A2 V1. That's going to be pi big R squared. I'm sorry. I'm going to do this different. Sorry. You could do it either way, but I prefer this way. Okay, let's V1. I'm going to express V1 in terms of V2 instead the other way around. Makes no difference. We come to the same conclusion. V1 is going to be A2 over A1 V2, which is pi little r squared over pi big R squared V2. All right, so then V2 is going to be, V1, duh, is equal to, it's really R over big R squared V1. Okay, well, I already know that R over big R is very small in front of 1. If you square a number smaller than 1, it becomes even smaller. So V2, this is V2. Can't seem to get my V1s and V2s straight here. Okay, so hold on. V1 is little r over big R squared, V2. This whole thing here is very small in front of 1. Like, it was already the case because of little r over big R, but if you square it, it gets worse. So this V1 is going to be very small in front of V2. Makes sense intuitively. I mean, look, if you have a huge tank, right, and you have a tiny spigot at the bottom, yeah, the water is going to come out very fast compared to how fast the level drops in the tank, because it's a huge tank. Okay, so V1 is very small in comparison to V2. Now, from there, the sloppy way to do it is to say, oh, well,
that means that V1 is approximately 0.
We can neglect it. I don't like that. If V1 is 0, V2 is 0, because guess what? A1 V1 is A2 V2. So the point is that we want to be able to neglect V1. In fact, even better, we want to be able to neglect 1/2 rho V1 squared in front of 1/2 rho V2 squared in Bernoulli's equation.
So if this is true, then I'm going to claim the following, okay, that V1 squared is going to be very small in front of V2 squared. And in fact, if I multiply by 1/2 rho on both sides, then I'm going to have 1/2 rho V1 squared is very small in front of 1/2 rho V2 squared. Okay. And that is typically the case if one area is very small compared to the other. And this is the conclusion that we want to come to with continuity, because this is going to be useful when I write Bernoulli's equation. It's going to help me simplify it, right? Now, there's another option, right? It doesn't have to be the case. Maybe the spigot isn't so small. Maybe I don't get to make this claim here. Okay, in that case, what do I do? Well, I still write continuity. I just keep this. I say, okay, well, you know what? The best that I could do is I got V1 in terms of V2. I'll sub that into Bernoulli later, and I'll solve for V2 that way. But this is going to be a little nicer because I'm going to knock out this term entirely in Bernoulli's equation. All right, so before I go set up Bernoulli's equation, let me just make a copy so that we can have it here and reference the situation as we write Bernoulli's equation. Okay, so Bernoulli's equation is going to be between points 1 and 2, P1 plus 1/2 rho V1 squared plus rho G Y1 is equal to P2 plus 1/2 rho V2 squared plus rho G Y2. Okay, Y2 is 0, so that's out. P1 is the pressure at the surface here. The tank is open to the atmosphere. The pressure on the surface is the surrounding pressure. That's PATM. Turns out, however, that P2 is also PATM. Now that's not as obvious, and we're going to kind of accept that one on faith. And we'll say that when fluid flows out into the atmosphere, the pressure in the flow is the atmospheric pressure. So then this is going to cancel this. They're going to go away. Right? What you're saying is that it's not pressure that drives the flow. Right? We said fluids go from high pressure to low pressure. Right? That's true if there's a pressure difference. Okay, but what you're seeing here is not something that is being, the fluid isn't being moved because there's a difference of pressure. It's actually being pulled down by gravity. So this is called a gravity flow. Right? There's no difference between P1 and P2. Like, however much P1 helps by pushing down, P2 opposes by pushing against, and it washes out, it doesn't make a difference. That's not why fluid flows out. Fluid flows out because it gets pulled by gravity downward and then out through the spigot. And so pressure goes away. Okay. So then I have Y2 is 0, Y1 is H, so this is rho G H is equal to 1/2 of rho V2 squared minus 1/2 of rho V1 squared. Okay, so we're back to neglecting some things in front of other things, right? We have this, okay, we know this from above, this came from continuity, and that means that if I subtract this from this, it makes no difference, right? It's so small in front of 1/2 rho V2 squared that you could subtract it out. Makes no difference. So that's going to mean that basically rho g big H is approximately 1/2 rho V2 squared. Okay, but it's pretty close. It's a really good approximation. Okay, so then rho drops out, and V2 becomes square root of 2gh, which should blow your mind, okay, because if you were wondering whether or not Bernoulli's equation was indeed equivalent to conservation of energy, well, here you have your answer. Square root of 2gh is by definition what you get with conservation of energy when you're looking for the speed v of something being dropped from a height h. So Bernoulli's equation truly is conservation of energy. I mean, technically conservation of energy per volume if we look at the units, but it works the same way, and it's the same kind of relationship that it's trying to bring forth between these quantities. And indeed, it ties with conservation of energy from before, where V2 is square root of 2gh. Okay, so that tells you what V2 is, which means that now we can compute the volume flow rate out of the tank because, well, we know A2 and we know V2, so that's pretty straightforward. Okay, so we did Bernoullian continuity, and that told us basically everything we need to know. Right? So a good idea is always to write both. And then here we're saying this is the spigot, right? And the water is going to come out of this thing. And we're saying, okay, water comes out at a speed V2 is square root of 2gh. And then this is a radius, little r, so this is A2 is pi r squared. And so QV, the volume flow rate flowing out of the spigot, is equal to A2 V2. That's pi r squared times square root of 2gh. All right, there we go.
And so, of course, it's not perfect because h, in fact, is going to change with time, and so your volume flow rate is going to change with time, but right when the spigot is open, that is going to be the volume flow rate coming out of the spigot. And so if we go back real quick, have a look at what we did. The problem of the draining tank is a classic problem. And it is usually the case that A2 is very big and very small in front of A1, making V2 very big in front of V1. Okay, but if it weren't the case, again, continuity at the very least will give us a relationship between V1 and V2, which means that we can then plug that into Bernoulli's here, so that now Bernoulli's is only a function of V2, and I can solve for V2. It's going to be a little bit more complicated, but it's doable. And typically, not every single time, but typically, your fluids problem, if you're talking about a tank or something like that, falls into one of those two categories. It's either the case that you can make this assumption and you get this, and then you get a simplification here in Bernoulli. That's really nice. Or you just have V1 in terms of V2, you plug into Bernoulli's. It's typically one of the two. Okay, but it helps to know that so that you know what to expect when you're reading through the problem and beginning to solve. But in general, you know, we only have two equations to describe fluids that are flowing, so there's a good chance that if you write both, you end up with the answer. All right, so that's it for fluids. In a sense, that's all you need to know, as in we've covered every single formula that you might encounter. Of course, you know, you got to go do problems and practice on your own and see different types of problems. There's more than these two problems, of course, in fluids, obviously. But as long as you can identify, is my fluid at rest versus is it flowing, and then what equations do I use accordingly, then usually you'll find that after doing a few fluids problems, you get a hang of it real quick. There's not much to this chapter, which is kind of nice, a nice break after 3 weeks of torque and rolling without slipping and all that stuff. So this is a bit more straightforward, and it's easier to get good at fluids in a short period of time. But it is worth doing. Certainly go do problems to practice and see how that goes. And then next week we'll be moving on to something completely different. So like it is, we're not going to see it again. We might see a tiny bit of fluids and oscillations if we go that route. Occasionally you get to problems that might mix the two, but for the most part, fluids is its own little thing, and once you've done it, you've done it. Right? And that's kind of how it's going to feel moving forward. That's what I was saying earlier. After this, it's oscillations, then waves, and then calorimetry, thermo. They kind of all go together, and each one is its own little thing. And so it's just a matter of sitting down and getting good at that little chapter, and then you move on to something completely different. So not much. That means that we're not going to go into great depth in each chapter, right? So it's not going to be like we did before, which is nice because we're nearing the end anyway. We got a month to go, tops. So we got basically 4 more weeks to cover whatever's left, and that doesn't leave a lot of time to start digging very deep into oscillations or waves or anything like that. So with that said, best of luck. I know most of you are studying for midterms right now, so whether it's physics or the 6 other midterms you have the same day that you have the physics midterm, because why would Berkeley know how to schedule things? Good luck with that. It's always a busy time. I realize that. This will be a short break at the end of the month with Thanksgiving, during which you will of course do 6 hours of physics a day, right? But more seriously, there'll be a short break, but then it's going to be really fast paced again. So we're just at that point where everything's going to be fast paced. But good luck. Keep doing what you're doing. It's not over till it's over. So you still have a chance to do well or to do better if you need to do better, or both. And I hope midterm 2 goes the way you want. And I'll see you next week again to move on and do oscillations. So in the meantime, let me know if you have any questions, and best of luck. Take care.